Hi everyone, and welcome to the second TIA Centre seminar of the academic year. For those of you online and new to seminars, my name's Adam Shepherd. I'm a postdoc here at the TIA Centre. And for these seminars, we try and invite people from across the globe to present new and exciting research. So today we'd like to introduce Dr. Yuri Tolkach. Yuri is an attending pathologist at the Institute of Pathology of the University Hospital Cologne, Germany, and a lead of the research group for AI applications in digital pathology. He and his team developed a number of diagnostic tools for different malignant tumours, such as prostate, kidney, colorectal, skull, lung cancer, and others, for quality control in pathology, and led the organisation of the Semi-Cold Computational Challenge. Yuri is a Vice President of the European Society of Digital and Integrative Pathology, and a Chair of the Scientific Committee of ECDP. The title of Yuri's talk today is Using Artificial Intelligence for Diagnostic and Prognostic Algorithms in Gastrointestinal Cancers. So thank you very much for joining us today, Yuri. And with that, I'll pass it over to you.
So yeah, thanks a lot for this kind of introduction. Yeah, thank you for the invitation. Really happy to be here today, and heard a lot about your group, and of course read a lot of your papers. And yeah, great to meet in person, and happy to present some data about our recent developments. So I would like to concentrate on two main algorithms we published recently, and one of the algorithms is about esophageal carcinoma, esophageal cancer, and another one is about colorectal cancer. I will start with the first one. So basically, this was a study. And the aim of this study was to develop an algorithm that can help pathologists to process the specimens of esophageal cancer. So maybe a little bit about my background. So I'm primarily pathologist, and therefore I will show more images and maybe will be more on clinical side. And of course, I tell some details about development, and maybe if you have some questions to more technical details, you can ask them later. So basically, this was our recent publication, and the following slides are exactly a little bit more detailed and sometimes more high level about this paper. So to start and to say some words about the clinical task. So you have probably most of you are more technical specialists or computer scientists, but in pathology we have a huge problem. Yeah, we have a lot of work and only few pathologists, so we always have huge overloads, and of course having some AI tools that can take some parts of the work from us will be highly beneficial. And at that, most of probably 70% of our work is very mechanical, like looking at slides, searching for some typical structures like tumor tissue and so on. So these are really the tasks that can be optimized and automatized. And esophageal adenocarcinoma, so esophageal cancer, is basically one of the areas where we developed algorithm. And why? It's because that the specimen that we receive with esophageal cancer are ones of the largest pathology specimens. So we have like sometimes up to 50 histological slides to analyze, and it takes, one case can take maybe 40 minutes, maybe 60 minutes, depending on the complexity. So the underlying task is that for many tumors, if you get diagnosed with a malignant tumor like prostate cancer, maybe breast cancer, in many situations the surgeons will just remove the tumor or organ with the tumor without any further questions. But for esophageal cancer, especially for esophageal adenocarcinoma, there is another approach. And this approach is that the patients will firstly have a so-called neoadjuvant chemotherapy. Neoadjuvant is a little bit scary word, but it's actually a very simple concept. So the patients receive some chemotherapy, some very potent anti-tumor therapy before the operation, and the aim of this therapy to reduce the tumor in size. Yeah, so to target something we call regression of the tumor. And then after this chemotherapy, hemoradiotherapy, sometimes it's also radiotherapy, we get these resections. So it's very small here, but it's like a specimen 10 to 15 centimeters. And then the peculiarity of the esophageal resection is that we have to completely embed the tumor or this tumor bed. So basically we produce a lot of histological slides with this tumor region, but also we have to include the lymph nodes. So sometimes you have extra 50 slides with lymph nodes. For each malignant tumor, you will normally remove some lymph nodes to stage the tumor, yeah, to detect if the tumor already spread to lymph nodes or not. So basically, our task was to automatize this diagnostic process. And here you see a typical histological section of esophageal resection specimen. So it's one of these 50 histological slides. And here you can see that there are different tissue structures. For example, this is a surface like mucosa. This is a deeper parts of the resection specimens. This is like something we call adventitia, so mostly fatty tissue with vessels and nerves. And here you have tumor tissue. So you can see here tumor tissue, it's not like a bulk, yeah, like a tumor node. It's like you have tumor here, you have tumor there, maybe here, and also there. So with some distances between the tumor. And this is exactly something that happens with a tumor after this chemo or radiotherapy before the operation. So it's regression. So basically, what we have here near the tumor is this fibrosis. So fibrosis is a word where you have just accumulation of connective tissue near the tumor. So basically, everywhere where you see this like a pinky stuff here, this was tumor earlier. So this was all tumor, like this one, but after this therapy, chemo, radiotherapy, you have only these remainings of the tumor or vital tumor tissue. So basically the task, the pathology task will be to calculate the percentage of this vital tumor tissue, like in this case, it's 10%. And based on this calculation, we will stratify patients into prognostic groups. So basically, the prognosis is extremely well in patients with complete or subcomplete regression. So we see only this fibrosis. So fibrosis is completely benign. It's not a tumor anymore. It's just a connective tissue. Or very few this foci of tumor. So basically, these are the patients that survive many years, but the patients where you have a lot of this vital tumor tissue after this therapy, they have prognostically unfavorable course of the disease. So basically, our task was to detect this vital tumor tissue and to calculate the regression score, like this percentage of the vital tumor tissue. And for this purpose, of course, you cannot just detect tumor and you cannot not only detect the regression fibrosis, because there are many different other structures like mucosa here and some nerves, vessels, and so on. You have to be able to process this tissue, you have to detect all these different tissue classes. So for training, we selected a cohort of patients. It was like 100 of patients with almost 200 whole slide images that we decided to annotate. So this was a large amount of annotations, like 1 year annotating of these slides. And this was actually a big mistake we made in this study, which we understood much later, because normally using the slides from only one department for training of the algorithm is not that great. So sometimes it's so that the quality of sections is really good, but in many situations you can, when you show me the slide from my department, I can exactly tell you this is a slide from my department because it has a certain quality of cutting, staining, artifacts. And this is exactly the case, that in our slides we have a certain thickness, certain quality of staining and cutting that was very special to our slides. So later when we trained the algorithm, we had to spend probably 4 or 5 months with different normalization strategies and training cycle GANs and so on to cope with this problem. But we also selected some data sets from other departments, from Austria, from Wiener Neustadt, also from Charité, from Berlin, and also took some slides from the DCGA. So the peculiarity of these slides is that these tumors were not treated before the operation. So it's like a domain shift, yeah. So they are slightly different, but we wanted to show that once we train on the on this pre-treated tumors, so this algorithm can generalize also to these materials, so to untreated tumor. And we also took another data set from our second lab. We are a large institute, have several histological labs to make like a prospective validation of the algorithm. So you can see here how the annotation like.
Sorry, Yuri, can I ask a quick question here? Sorry, on the last slide.
Yeah. Mm-hmm.
So yeah, my question was, so in one of your slides previously, you said that you get to sort of 50 tissue slides for each section. Sorry,
Yes.
for each yes. Yeah, exactly. So how do you go from those sort of 50 slides, just getting 2, for instance, for that particular data set? Is it only 2 of those slides that are particularly representative of the problem, or is it, and that 48 might have unnecessary tissue, or is it?
Sorry, Adam, I unfortunately acoustically cannot understand very nice what you asked. Maybe you can.
That's okay. So my question was, so on this slide here, it says up to 50 histological slides for my case. And then on the next slide for the cohort, you've got roughly 2 slides per patient. So I was just wondering how you go narrow it down from 50 slides to 2 slides. Is there only 2 slides out of those 50 slides generally that are roughly important, or is it?
Yeah, so basically, of course, the annotations really annoying work for most of us pathologists. So we just decided to go through all these cases and to select the slides that are the most representative for these cases. So you probably do not need to take 25 slides per case. It's always better when you have like 1, 2, 3 slides per case, but you have more cases. So it's the basic strategy. You probably, if you take one patient and I don't know, maybe 20, 30, 40, 50 slides, the tumor will be very similar in most of these slides, but also a little bit different from time to time. So you just take this, you pick this heterogeneity, but you take only 2, 3 slides, because, you know, if you annotate all these slides, 50 slides per patient, and you take a cohort of 100 patients, you probably will not be able to accomplish this project in the next 10 years. Yeah, so it can be really very difficult.
Thank you. We've also got a question from Nasir as well.
Hi, Yuri. Just a quick question from me.
Yep.
So when you do these annotations, what are you annotating? Are you annotating the fibrous area and the fibrosis area and the tumor area? Oh, like that. Okay, great. So you're doing all of this to quantify the vital tumor, essentially. That's what the purpose of the annotation is, right?
Yes. So the purpose of annotations, so there were 2 different tasks in principle. So basically the first task was like create an algorithm that can, without any restriction, restrictions, process all these whole slide images and to stratify different tissue classes. And as a further downstream task was like quantifying the regression score. And the regression score is practically the percentage of the vital tumor tissue divided by vital tumor tissue and regression fibrosis, the whole area of the tumor.
Okay, great. And then my second question is this very interesting TCGA part that you have included to the study as well, 22 cases. And for those, what is it that you're trying to measure, trying to estimate? Because there is no neoadjuvant chemo as you mentioned, right?
Yep. So we validated these two different subtasks like tumor detection and detection of all other tissue classes. This was like a first part of validation, and the second part of validation was actually validating the regression classifier. Yeah? So for TCGA, we validated the quality or accuracy of detection of all tissue classes, with except of regression fibrosis, because there is no regression fibrosis. So we can only estimate the specificity for regression fibrosis. Like other tissue classes were classified as regression fibrosis, then it's like problems with specificity of the algorithm. But of course, we cannot calculate sensitivity on this data set because there are no regression fibrosis in these slides. But for other classes, like for tumor detection, which is also important, for example, you have normally all these specimens are on the intersection of two different types of mucosa, like gastric mucosa and esophageal mucosa. These are two different types of mucosa. Yeah? And if you detect gastric mucosa as esophageal mucosa, or vice versa, it's not that big deal. So it's not a big problem for pathology work. But if you detect a normal mucosa as a tumor, then it's another story. It's like already a real problem. Yeah. So I will show some metrics on the TCGA data set and the several slides. Maybe just shortly mentioned, I mean, annotations, it's probably the most important part of the projects because the quality of data sets is always decisive for the performance of algorithm. And I would say we will never make annotation that way. Yeah. So normally we do the annotation in a little bit different style. I should say this was our a major work of us, but it was a work in the real beginning of our, we have many large projects to different tumors, and most of this, so we never trained classification algorithms, and this was exactly a classification algorithm, so it was a page level classification, and now we have to change a little bit annotations to correct annotations and so on to change this algorithm into the segmentation one. So the annotations were really precise, but you know what we will never do right now? So you can see here, for example, you have here tumor, black is tumor, this is mucosa. And for example, you have tumor annotation here, you have tumor annotation there, and there is nothing around. Yeah. And when you have nothing around, so you don't make these dense annotations. So for segmentation, for classification algorithm, it's okay. Yeah, it will work. But for segmentation algorithm, it's always better. So you cannot make dense annotation of the whole slide. So normally you select a region, but in this region you make dense annotation. So that's our typical annotation style for segmentation models right now. Normally, if you train on this data set, a segmentation model, it will have problems. Yeah, so it will not, especially these borderline regions between different classes will be not that precise. But anyway, it's already a accomplished project. You kind of learning, but it was a lot of learning by doing. And the problem why we decided to train a classification algorithm is because at that time we had almost no experience with segmentation algorithms, especially how to balance, how to oversample, and how to exclude non-annotated regions from training, like ignore index, making ignore index. That at that time that was not perfectly clear to us. For now, I would say we are very experienced in training diagnostic algorithms, really precise segmentation algorithms. But at that time, everything we could was classification algorithms, and that is the reason why we did the annotation in that way. Again, for now, I will never do such form of annotation. They are precise, but again, classification algorithms, so patch level algorithms, are just no go for most diagnostic tasks in pathology. So it should be a segmentation. Yeah. But anyway.
Thank you, Yuri.
These are all the different tissue classes we annotated. Of course, the most important for us were tumor and regression, but I should say we had a very substantial amounts of annotation of different other classes. So you can see here a constellation of training and test data set and patches. And so for training data set, normally for all algorithms we train, we do some overlap. So we have a positive experience when we do less than 50% overlap, like 20-25% overlap between single patches. But normally for test data set, we don't do this, like you don't need this. So here was an overlap of 50%. So it's like a little bit, so if you do this without overlap, that would be probably like 300,000 pages or something like that. So these are the pages. I think later I have also an image. So these pages were extracted under magnification of 10x or micron per pixel 1.0, approximately 1.0. And these are the pages and examples of the different tissue classes. Yeah. So we had, as usual, when you use external validation and external data set from different departments, you have this huge data set level heterogeneity. And this is our own data set. And as I mentioned, we had a difficult time trying to make the algorithm more generalizable to other data sets. But at the end, with these additional strategies, we managed this problem. We also had to include more. So I think when we started training, and then when we had this problem and started using different normalization strategies, so we decided to make more annotations, so extended data sets. So it was like 5-6 months where we were just looking for a solution to the generalizability problem. So basically, this is a I don't think that this algorithm is very challenging from the technical point of view. So it was like very simple approach, inception ResNet v2 model with 11 tissue classes, patch level classification. As I said, we used 3 different approaches with data augmentation and also with like stain normalization with style transfer and stain transfer using Nasenko principle. So these are the different metrics for validation using test data set. So basically, this one is like an internal test data set. So it certainly has some similarities to the training data set. These are completely independent data sets. So it was, I would say, rather high sensitivity and specificity, and in principle, let's say as pathologists, we were pretty happy with the performance of the algorithm. Yeah. So this is an AUC area under receiving operating curve, sensitivity, specificity, accuracy, precision, recall, F1. Now how it works. So this is a slide from Austria, from one of the test data sets. This is a slide from the TCGA, so basically a therapy-naive tumor. And here you can see in green is tumor tissue, blue regression, and we have here also muscular tissue, so muscularis propria, and also mucosa. Here you can see some patches which are blue colored. It's like detected as regression tissue. I should say that was mostly like fibrosis area. So you normally also have some fibrosis or stromal dysplasia in tumors. So it's basically, if you ask human pathologists, like, okay, is this regression or is this not regression? Probably no one will be able to clearly differentiate if it's not known that the tumor was not pre-treated. Okay, so with this algorithm was then.
Sorry, Yuri, do you mind if we ask a quick question? I think the sitter's got a question.
Just on that very point, Yuri, you mentioned that it would be very difficult for a pathologist to say uh, which bit of the tissue was regression tissue and which one was original tissue, so to speak,
Yeah.
right? Tissue that would have been there without any treatment. How do you address that challenge?
So yes, so I would say what I wanted to say, but maybe I explained a little bit not in the right way. I mean, when you show the pathologist only small regions like patches, it will not be possible. Yeah, but you show a little bit of context, so you can see what is around here, how it looks like here in the regional level. So it's of course much easier, but still there were some regions. Let's say when we made annotations, it was always a question, okay, is it a regression or is it just like a little bit fibrosis or just normal connective tissue and so on. So there were certainly some regions where even experienced pathologists cannot tell exactly. Of course, context helping, but not on all not in all situations. However,
Sorry, go ahead.
Yeah. So basically, we tried to exclude these regions from annotations, so unclear regions from annotations, and yeah, at the end, it worked actually very well. But of course, let's say we made a small experiment later. When you get these patches or classify these patches, you can play a little bit with a threshold, like, okay, this is a 95% probability it's regression tissue, or maybe it's only 20% probability. And we saw that actually when we change this threshold in a wide range, the algorithm is pretty robust. Of course, you have some patches classified no more as regression fibrosis, more as connective tissue, and so on, but it was not affecting the final classification because these uncertain regions were mostly like, for example, here you can see these single patches. So I don't think that these actually regression fibrosis. I think it's like a false positive result here because it's like a fatty tissue with some vessels. Maybe there was some faint fibrosis that was captured by the algorithm, but you never know if it was tumor induced, or therapy induced, or something different. But again, I think it's just problematic, and the algorithm is so good, so far good as the training data set good, and we really not just blindly annotating, okay, this is regression fibrosis. We really asked ourselves, is it regression fibrosis, and tried to do our best, and also asked their experience. So we have one of the German experts on esophageal cancer. We have some in Germany. It works in our department. So we discussed a lot of cases with him, and at the end, try to do our best for generating ground truth. Yeah.
Okay, thank you.
But of course, there is like there is nothing where what you can use like immunohistochemistry or something like that, where you can objectivize the regression. So tumor you can. So tumor is easier, but regression fibrosis, it's like also the pathologists had the same problem. Yeah. Yeah. So basically, this algorithm should be applied to the whole cases. And this is exactly the example of a small case where you can see how the regression score will be calculated. So we just take the tumor area, regression area detected by the algorithm, and we have area, tumor, and regression together, and then we calculate the percentage of vital tumor tissue, like 7.5% in this case.
Can I ask another question here again? So on sort of the first slide, it's sort of implied that when you do like this regression score in clinic, that it's the tumor within, sorry, it's the percentage tumor within the whole of the regression area. Is that what you're still doing here, or is it just literally the complete area of tumor and the complete area of regression and then the ratio? Or so I'm just asking whether that makes a difference or not.
So basically, this is a typical regression scoring. There are two different forms defined by WHO. One is Becker score, which is used in Germany, and another one is Mandart, more popular in the United States. And we just follow the classical rules of regression scoring. So you have to define this area of regression fibrosis plus tumor, and calculate percentage of only vital tumor tissue to the whole tumor region. Yeah.
Okay, thank you.
And
we've also got a question online from Simon. He said, "Hi Yuri, is the regression score also dependent on how the tissue is cut? I.e., if it is taken from the middle of the tumor, would you get a lower regression score?"
So one of the first slides was this high-level overview how the specimens are being processed, and it's like a guideline, or it's like a rule that we will embed the tumor region completely. So we don't leave anything aside. So it will be systematically from upper to lower part completely embedded. And so basically, if I, for example, take only here from the middle, there is no tumor tissue, only regression fibrosis, then it will be like a full regression. And if I take here, it will be like not a full regression. So you actually have systematically processed the whole tumor. Yeah. Not whole tumor, but whole tumor regions, because sometimes you do not find any tumor. So there is a category of patients with a complete regression. So you find only regression fibrosis. Yeah.
Brilliant. Thank you very much for explaining.
Okay. So then we started our more clinically oriented validation. So first of all, we took approximately 100 cases, historical cases from the archive. And these cases were processed by 12 different pathologists. Some of them were experts in GI pathology. Some of them were not experts in GI pathology. So it's like just a whole team of the pathology institute that at some time point processed these cases. So in Germany, I don't know, I think in UK you have like a subspecialization. For example, if I am a genitourinary pathologist, and I will, oh wow, then I will I will work only with GU cases. In Germany, we have to work with all possible cases with small exceptions. So basically, what that mean do you see that blue line?
Yeah, I do see it. I'm not sure. I don't think it was me.
Okay. So I don't know how to remove it. Anyway, so basically we use this AI tool on all these cases, and this was like 1,300 slides in general, but we also just extracted the regression grading from pathology reports. And now we talked about percentage of vital tumor, but actually when you write a report, you will not only provide the percentage, but also classify as one of 4 different grades. So grade 1, regression grade 1, it's like more than 50% of tumor is vital, so it's practically a non-responder. Regression grade 4, it's like a complete responder, you don't find any tumor. And should we get rid of this blue line? It actually seems to be on my side, but you see it. You see this blue line as well, yeah?
We see it, yeah, but can't seem to find a way to get rid of it.
Okay, it's very strange because I never saw this artifact before. maybe I stop share and do it once
Yeah,
more.
let's try that. Thank you.
Okay, it's not there. Okay, so basically we for reporting purposes, or according to this typical Becker system, we will stratify all the patients into the 4 regression grades based on this percentage of vital tumor tissue. And now what we found out that there were 6 cases found by AI algorithm with a tumor which was missed by pathologists. So in 6 cases, there was a vital tumor tissue, but pathologists said it's regression grade 4, so complete responder. There were also another case where pathologists said, okay, it's a tumor, vital tumor tissue, but algorithm said, okay, it's not a tumor tissue. Then we reviewed this case with experts, and the conclusion was it's not a vital tumor tissue, it's like a pre-neoplastic lesion. So basically, we were able to identify the cases where you have immediate benefit for the application of such algorithm. But when we remove this true reclassifications, we have kind of quadratic kappa of 0.74. 975, so it's basically for typical gradings, independent of organ, it's considered to be a relatively high agreement level. Yeah. What we also found out is that we reviewed this issue in all details. That here we have these 22 cases where pathologists had regression grade 2. So it's basically between 10 and 50% of vital tumor tissue, and the algorithm said it's less than 10%. And this is actually, after we reviewed all these cases, we were on the side of the algorithm. And the reason for that is actually that when we as humans, so it's like such an psychological effect. So for example, if I have a slide, 1 slide or 2 slides where I have a lot of tumor, it stays in my memory like I have a lot of vital tumor tissue, even if all other slides are completely free of tumor. And this leads to the overestimation of the percentage of vital tumor tissue. And this is something we saw even by experienced pathologists. So when we reviewed all these cases, it was really like a surprise. Okay, when I kind of have all the slides on the display, I can see exactly where the tumor is and where regression fibrosis is. They all came to other results. So they basically went into the direction of the regression grade 3, so to the major responder. These are minor responders. So basically the human, of course, like reconstructing quantitative parameters from to 20 to 50 slides is very difficult. It's something we know also for prostate cancer Gleason scoring, on all other such tasks in pathology. So I think that AI algorithms have huge potential for all quantitative tasks. Yeah. And then we also made a small experiment with 20 different cases without AI assistance and with AI assistant. These were 3 pathologists, myself, Professor Quas, the expert I mentioned already, and also 1 other experienced pathologist. And we saw that actually when we use AI assistance, so we have much more concordance between each other. So we actually, I would say that it's not like trusting the algorithm, but it's really the algorithm really making the things more objective to us. First of all, when you take a slide and look at it under the microscope and then take another slide, and so 50 slides, so you really cannot reconstruct this in your head. But if you have everything on one display, like easily shown to you for all the slides, so you can make much more informed decisions. And I think that yeah, again, it's a benefit of using such algorithm. But another benefit was
Wait, do you mind if I just ask another question there? Sorry.
Yes.
So in terms of with AI assistance, so do you show them the segmentation map, or is it a score, or is it the actual grade, or is it all 3 of those things?
The shown was the segmentation maps for all slides. So basically how it works, so we have the overlay of the segmentation map. So it's not a real semantic segmentation map, but with this more page level segmentation map. And the pathologists look at H&E section and then look at the map, and so basically check if the algorithm was right, detecting tumor and regression fibrosis or no. And at the end, they have a kind of suggestion from the algorithm based on these maps. It was like 7.5% vital tumor tissue. And then basically, if you saw, okay, there were 2 slides where it was a little bit more fibrosis detected by the algorithms, and I'm not agree, then I can, for example, say, okay, it was not 7.5, but it was like, I don't know, 8. Yeah, so you can always correct correct your the suggestion of the algorithm.
Brilliant. Thank you for clarifying.
Yeah, and basically this is one of the most important parameter for us as pathologists, time per case. And you can see here, so basically these are 20 cases without AI assistance and 20 cases with AI assistance, different number of slides with tumor, so all resection margins and so on, they were excluded. And you can see here, for example, there are some cases where you need like 12 minutes per case, sometimes 10 minutes and so on. And here you can see, so here the upper bound is 10 minutes and here 15 minutes. And if you kind of reconstruct, so you can see that actually you need only several minutes per case with AI assistance, while without AI assistance, in many cases, you need 5 minutes or more. So it's basically, it was like you need 2.2 times less time for analysis of single cases. It's a real improvement for us. And at the end, you have higher precision. And you have also additional prognostic value, and these are exactly this slide about. So basically, why do you do this regression grading? So probably for the patients after the operation, there are 2 major prognostic parameters. And the first one is if there are lymph node metastases, vital lymph node metastasis. And the second one is regression grading. So based on these 2 parameters, many further therapeutic decisions will be made. And this is this regression grading of the pathologist, of this group of 12 pathologists, so basically the information extracted from the reports. And the end point is overall survival of the patients after the operation. And basically, these regression grades are supposed to stratify these patients. So regression grade 4, no vital tumor tissue, complete responders, clearly this is the best prognostic group. And then regression grade group 3 should be above regression grade 2, and regression grade 1, it's the most unfavorable. But you can see here that actually this is a known problem for regression grading, so that this prognostic stratification is like suboptimal. And basically also our surgeons and oncologists said that they will more rely onto this stratification of complete responders and all other patients, yeah, like these 2 groups. Because in this grade 1, grade 2, grade 3, even in experienced hands, so this was a group of 12 pathologists. So if you take an experienced GI pathologist, it will be much better stratification, but still you evade much more prognostic value from this stratification. And then we looked into the into our quantitative analysis, and actually were able to identify 2 new simple prognostic parameters based on quantitative estimation of regression fibrosis and tumor volume. So basically, if you take the areas of regression fibrosis, and if you take the areas of the residual tumors, so vital tumor tissue, you can reconstruct the pre-therapeutic tumor volume. So this one, pre-therapeutic tumor volume. So basically the size, the dimensions of the tumor before the chemo or radiotherapy was initiated, so at the time of diagnosis. And basically this parameter showed very high performance for the prognostic stratification of the patients. So basically, the patients, the patient that have larger tumors. So again, we don't say, okay, the tumor was. So at the time of the operation, we have only residual tumor. So it can be like very small residual tumor, but initial tumor volume with very high, yeah? And we can detect this with our algorithm. And so basically these patients with initial large tumor volume, reconstructed, they perform prognostically worse than the patients with smaller tumors. And we also tried to make the same for absolute volume of residual tumor tissue, so like absolute volume of the vital tumor tissue in the resection specimen, and it was also prognostically more impressive, let's say, than the regression grading, but it was not that statistically significant. It was like a trend to statistical significance. Yeah, but this one is something that we are going to prospectively validate, because we really think that so for humans it's like an impossible task. Like when I say, okay, here are 20 slides, please reconstruct how big the tumor was before the chemotherapy. It's just impossible. But for the algorithm, it's a very easy task. So basically all the quantitative metrics necessary for this reconstruction are available. And so this is something we would like to validate in our prospective study, because this can have real clinical impact. Because these patients, like who have worse prognosis, these are the best candidates for their therapy escalation post-operation. So normally after operation, after resection, you just make like active surveillance, and if you see there is a recurrence, then you will you will perform some additional therapeutic manipulations. But these are the patients that might benefit from immediate therapy escalation after the operation. So it's probably one of the major findings of our work. Yeah. So this was my last slide about the esophageal cancer. I actually have some slides about colorectal cancer. Do we have time, or it's already? I think I was too slow with the esophageal tool.
So we've got just under 15 minutes left. So it's up to you really, how much you think we can get through, or whether we can. Nasir's also got a very good question for you.
A quick question on the previous slide. So I noticed that your overall survival rates for a lot of these cases are quite reasonable, quite high actually, as compared to other oesophageal adenocarcinoma cases that I have seen, where the survival is really, really poor. But maybe that's because we were working with advanced stage inoperable esophagogastric adenocarcinoma. In this case, I see 50% survival after 6-7 years, and even on the right-hand side, about 75% survival after the same amount of time. Was there a particular grade of cancer that you worked with? Your kind of inclusion criteria, did it include any late-stage oesophageal carcinomas?
No, we did not do any pre-selection with regard to stages. So I would say maybe it's too optimistic, but so we are one of the largest and probably most qualified centers in Europe for treatment of esophageal carcinoma. So we have like 300 or 400 operations, so 3 resections per day. And the oncologists and the surgeon that work here, they are really very competent. So like this might be one of the. So I don't think we have any pre-selection for the stages or grades of the tumor. This was relatively balanced cohort. Yeah,
we should be sending our cases to Cologne. By the way, did all these cases receive the neoadjuvant chemotherapy?
Yes.
All of them. Okay.
Yes. So this is a cohort of
Maybe that's a factor.
So this is certainly a factor, but I mean, this is a state of the art. So normally all patients, so at least as far as I know in Europe, this is very typical. So all patients with the esophageal adenocarcinomas become the neoadjuvant. There are two main regimes of therapy, with and without radiotherapy, but this is a standard of care, so they all receive this. Yeah, at least in Germany, it's like state of the art. If in UK you don't have this as a state of the art approach, of course this may be but as far as I know, it's like basically all of them. So we see like 2 cases a year that were not therapy, just because it was like an emergency operation with like perforation or something like that. Yeah.
Maybe it's just the other cohort I was working with was quite late stage. Thank you, Yuri.
Thank you. So yeah, we've got just under 10 minutes left, so it's up to you really how quickly you think you need to get to the slides, or
Yeah, I think actually probably I will just I can understand this was a lot of information. I think it will I think you have to digest it, and when we speak about a totally different entity, also I know that colorectal cancer is mainstream for you guys. So but anyway, this is already a published work. It was published maybe 4 weeks ago in the Modern Pathology, so you can get all the details. And it's basically no more a classification, like very precise segmentation algorithm that we use as backbone for more advanced applications like single cell analysis and different molecular genetic correlation and so on. But anyway, if you are interested, please check the original publication in Modern Pathology, and I think it makes more sense than talking about this in all details right now. Okay, thank you very much for your attention, and I don't know if there are some other questions.
Yeah, well, fantastic. Thank you very much for a really interesting talk. So yeah, we'll open the floor now to questions. So has anyone in the room got any questions they'd like to ask? Okay, so I'll start us off then. So my first question really is, so obviously this has been on esophageal cancers. So adenocarcinoma, sorry. How do you think the model will generalize to other types of adenocarcinomas, such as colon? Is it the same model pretty much that you were going to use then, or is it?
You meant to generalize to other tumors?
Yeah, so, based on the same model, yeah.
Yeah, we're actually making a small work right now. So we have very potent segmentation models for many important tumors like lung cancer, both subtypes, prostate, colorectal, kidney, breast cancer. They are all based on very high quality annotations, really pixel-wise segmentation. And we are making a study right now how it generalizes to different, like if we take breast algorithm, how it generalizes to prostate cancer. And we did this for colorectal and esophageal. So we saw that for colorectal cancer, algorithm, so in approximately 70% of cases, actually these were not so these were therapy naive cases. So these were not cases after this neoadjuvant chemotherapy. It was like you can really get a very high quality segmentation of the tumor and tumoral stroma. Yeah, so it basically can work as like a backbone algorithm for further tasks. But in 30% cases, it was not that great, because stroma is too different, or like tumor cells, tumor glands are too different. So it's obviously out of distribution. It's not working very well. Yeah? But for example, lung, we have lung algorithm that is both for adenocarcinoma and squamous cell carcinoma, probably the most precise segmentation algorithm we have. And it's actually also works pretty well for the for the esophageal adenocarcinoma, so it can really good segment glands and stroma. Yeah.
Oh, brilliant. And is all the data? I think I read that the data is publicly available now, is it? Or and the code or?
For colorectal, so no, the algorithm is not available, unfortunately, but many of the data sets were shared via Semicol challenge. So at least there are, I think, 20 very well annotated slides from two different cohorts, and also a lot of weekly labeled data. So basically, you can already try with semi-supervised learning. And so, I mean, colorectal cancer is relatively easy diagnostic task when you are speaking about tumor versus stroma. So I probably not need. For example, for our algorithm, we used 241 slides. It's like 18 months of annotation work, and probably you don't need so many slides. So you, if you really select, so you like annotate 50 cases. You train the algorithm, and then you like select only the cases where the algorithm performs not that great and annotate them once more time, like active learning, but not active learning, just selecting for annotation. You will probably can build a very nice algorithm with like 80 slides or something like that. Yeah.
Oh, well, sounds brilliant. And so, have we got any more questions from anyone in the room, or we've got a question from Simon Graham over here.
So on your segmentation work in colon, so you said at the start that you were annotating by hand, but then you can't physically annotate everything unless you've got something like active learning. So what kind of strategy did you find worked in practice to deal with that? So you mentioned just excluding the unannotated regions, for example. I assume you just had a weight of 0 for those regions. But what kind of strategy did you find that seemed to work well to deal with unannotated regions? And in particular, did you find that any submissions to the semicol seemed to work in particular for handling those kind of areas?
With regard to non-annotated regions, so we just exclude them from the calculations of loss. So it's a typical approach when you work with. I think we tried all possible loss functions, but for now we work in most cases with categorical cross entropy, and in native implementation in PyTorch, it's already have ignore index. You can use it, so we have, I mean, you anyway you have to weight or balance the classes. So there are different approaches. For example, we in some of our algorithms we used batch-based weighting. So we basically in every batch we calculated the areas of different classes and calculated weights. But in many algorithms we just worked with global weights for the whole data set, and it worked pretty well. For example, for colorectal cancer, and for batch level weighting was not that beneficial. And so basically, if you make like kind of regional dense annotations, these non-annotated regions are mostly not a problem. I think the most important thing is probably it really gave better results in of all our algorithms. It's balancing classes, so like trying to make balanced batches where you have representation of they should not be like the same area, for example, for tumor and stroma, but all classes should be represented in batch in a single batch. Like it brought the most benefit, I think, for the training segmentation models. Yeah.
Fantastic. Well, thank you very much, Yuri. And I think with that, we'll call an end to the seminar. That's been really interesting, and thank you very much for joining us. We wish you and the lab the best of luck in the future. So for everyone online, thank you for attending. And our next TIA Centre seminar will be on Monday, the 6th of November. We'll be joined by Anglin Dent online from University of Toronto. So yeah, hope to see you all then. But thanks again, Yuri.
Thank you for the invitation. Bye-bye.
See ya.
Thanks, Yuri.
Bye.
Bye.